This conference will now be recorded.
Okay. All right. Thanks, everyone. So a bunch of folks and I have been working on this idea of a reference architecture specifically for HPC for the past few months. And this is one of those rare talks with two titles. One is this idea of a reference architecture for the open chiplet economy, and it is part of a larger effort tied into Professor Ayer's work from UCLA and SEMI on a manufacturing roadmap for heterogeneous integration and packaging. And this is a group of people that collectively form what's called the third technical working group, one of four in that effort. And this group focuses entirely on open standards. There's a list of people who've been active participants, Anu among them, so she can keep me honest. Um, And what I do want to say is this deck has gone through. So the final presentation or the mid-year update for Mr. Heap is on Monday. I wanted to take an opportunity for a dry run and run the thoughts and work by all of you to see if you had any feedback that I could use before Monday. There's a bunch of things adjustments I've made at the last minute. So if you see any errors or howlers, they're all mine. So don't please don't associate them with the nice people who helped out. So what I'm going to do is talk about the effort a bit, then go into what we're saying is the case for package modularity, then develop a reference modular chiplet architecture based off a modern supercomputer called Fugaku, and talk about options for scaling, and finally where we think this has to go next. As always, please interrupt me at any point, and with any questions. It's much easier than sort of talking into a vacuum. So that's it. Any questions before I move on to the next slide? So the overall, there was a gentleman from Meta who had this very nice formulation, sort of establishing a quick start guide. So Mr. Heap, which Mr. Heap, the whole effort adopted, which is essentially this manufacturing roadmap is an effort kind of tied to the CHIPS Act, sponsored by NIST. And the idea is, what if we wanted to bring packaging and assembly back to the United States? What do you how do you guide people considering? How do you guide entities considering a factory? Um, And the basic assumption is that you're not going to be able to reshore packaging by replicating a successful workflow from abroad, but you need something else that's technology centric and that uses a lot of automation. There are four working groups in this effort. The Our working group is focused on products where actually all working groups are focused on products where packaging costs are significant, those that require advanced packaging technology. And the general intent is to go for what you'd call cost efficient mass customization. So how do you make high product mix, low to medium volume production, and can we develop standards for modularization and thereby room for automation? All the groups together sort of decided to focus on HPC AI for starters. And then the other groups, other twigs are also looking at high-end medical. Our twig isn't. And maybe later, if you have time, aerospace, defense, and automotive, because these have very complex products with a lot of compute, etc. So coming back to our group, the Twig 3, the sort of why for us on this call is pretty straightforward. Well, the obvious one is it is NIST that's commissioning the effort. The general intent of why we're doing standards is the idea is more innovation, that you would have easier, faster products, more robust, validated protocols and specifications. And more importantly, you can leverage the system to complete your product in a way that you couldn't if you're building everything yourself. The general idea that we're sort of hunting around on, poking around on, is to modularize the package that chiplets go into, and then maybe can we modularize the package? And what we mean by that is by develop guardrails for what's acceptable, what's in, what's out. As a starting point, the thinking is that we'd pick an existing module like an OCP HPC, OCP NIC 3.0, or some kind of modular hardware. Or virtually every supercomputer today is node based anyway, so there's a natural starting point. And we bound package performance throughput so that we meet the requirements of this systems module, and we translate those bounds into expected package requirements. Um, that's roughly the path of what we wanted to go on. I saw Anu before I started presenting, and if anybody else is from our Twig 3 zone, if you'd like to comment or say something, please feel free to interrupt me. Anu, anything else on your mind and that I should have covered?
Nope, I think you're doing a fantastic job.
Thanks. So what we also came to was that open standards, the most of the attention, I'll expand on this in a bit, is that generally when people focus on interoperation, and our group, as we're happy to say, is doing a lot on everything for open standards, right? Not just the data path, but they also matter for the control logic, DFT, physicals. They matter for information exchange, which is where all our wonderful CDXML stuff kicks in, package design, yield, etc. And they also matter for modular design. How do you sort of say these are the form factors that assembly and manufacturing should support? And by open standards, essentially we mean things which are freely accessible and usable. They could be single vendor standards if they're widely adopted, or they're community developed standards like ours. Um, and then we're sort of not going after that processes that support standards. We're sort of putting that off to later. It's not even clear that we'll ever get to it. But our general interest is in standards which are focused on assembling products for now. So most of our thought processes sort of ended up being oriented around this basic idea that chiplets need a new integration across the value chain, right? And the fundamental fact of chiplets is chiplets don't fly solo. You want to build a chiplet-based product, you need other chiplets you're going to talk to in order to build a complete ASIC. And what that means in practice is that there's a whole bunch of downstream factors which you don't consider when you're developing a monolithic ASIC that are brought forward compared to traditional design. The first and foremost is you're looking for other chiplets you're going to interoperate with. In terms of your own manufacturing cycles, you're looking for their inventory and lifetime. When you choose to design and manufacture a chiplet, you're also effectively choosing a packaging technology to go with your chiplet. The way you test and your at wafer sort and the fully packaged product changes, and obviously packaged product volumes matter in terms of your package design, etc. The basic thought process is that standards can help coordinate products across companies. Right, this is something that there's a concept that we have highlighted multiple times in terms of when we started thinking about this idea of open chiplet economy from a few months ago. So where do we stand on standards? This is my take, and I could definitely use some feedback here. Is that really there's a lot of activity on die-to-die FIs, a lot of activity on die-to-die transactions, decent amount of activity on chiplet and package test. And thanks to us, primarily, we've really gotten chiplet descriptions going. I forgot to add, TSMC is not an open standard, I believe. Um, this power models, SEMI has some device traceability work that can be expanded to chiplets. One of the interesting things in my head, and I think our group believes as well, is that there's very little on guardrails for packaging and assembly. There are almost no constraints on chiplet size, no constraints on power delivery. What kind of power you have to? What are the requirements? What are the what's the max power you can deliver to a chiplet. There's no constraints on thermals and wiring density, mechanicals like bump pitch and stresses, and bump and assembly pitch guidelines. And all of these matter. These are the things that matter to bounding, packaging, and assembly complexity. Um, and if you can address this, then you can sort of have a much better handle in packaging and assembly complexity. Any other? Does anybody have any idea of any particular standards or areas that I've missed? I sort of deliberately left out things like reliability, where you can sort of say this applies to a regular monolithic devices and can be extended to chiplets as is.
Very hard to work on standard, or but something that's probably getting to get more attention is reliability as well. I just want to throw that in there.
Yes, I will. And I was thinking of reliability. I did put in mil spec, and then I realized I hadn't heard of something unique to chiplets. I'd heard of general reliability standards that could be extended to chiplets, if that makes sense.
Agreed. Yeah.
Bape, when you're talking about the thermal guardrails, what do you have in mind? Typically, there's going to be specs, right, for data center, for industrial, and so on, and the final system has to meet that. So,
Well, I'll give you an hold that thought, and I'll give you something, at least a very simplistic model, and what we did with that model in about 15 minutes. Um, yeah, again, so what we think is that roughly, if you can develop a reference architecture. Sorry, any other questions before I jump off this? So David, there's one specific thing we use in terms of thermal guardrails, and I'll come to that if you, in terms of at least how we've used it in creating models. So what can you, and our thinking in general is that if you can develop a model reference architecture, a reference chiplet architecture, it can deliver all these things. Can kind of say, hey, this are the max number of chiplets sizes and types this architecture supports. There's a max package size this architecture supports. As a power dissipation, this is how much heat you can dissipate per millimeter square. This is the bump pitch and wire density your interposer or your laminate package needs to support. These are the largest chiplet sizes you need to support. In this is how big your package is. And you can also start thinking in terms of reference designs for your interposer. So the interesting thing is, what sort of catches my eye about HBM is that because it's been stable, you know exactly how big HBM is, you know what the IO size of the IO is. It's been stable for so long. Designers can plan their own product physicals around HBM. So in some sense, if you can deliver a reference architecture, can designers now form their own product plans around this reference architecture? And the idea that we went off, thanks to John Schaff from LBL, who sort of kicked us in this direction with some with a solid catalyst. So we can work off HPC A6 to develop a reference architecture. So you can sort of say functional modularity is intuitive in the sense that you can say, look, I've got a CPU, I've got memory, um, I've got I/O, etc. The key question is, can you do physical modularity? Can you do physical modularity in a reference architecture? And that's what we spent. So what I'm going to do is take a little detour to argue that yes, you probably can do physical modularity. So I think John Schaff isn't online, is he? Okay. So Fugaku is like a recent high performance computer. I think it's either still number 2 or number 3 in the world. And the Fujitsu has been remarkably generous in sharing public details. And the heart of each node is a high performance ASIC, which for our purposes, this is a reasonable abstraction. It's a collection of 4 compute complexes, each with their own HBM memory, and and the ASIC as a whole has a high-speed network that they call tofu and a PCIe controller, PCIe I/O, and the 4 compute complexes and the I/O to the ASIC are linked together by an internal high-performance network. And we know roughly that the die from publications is about 400 square. It's about 122 watts, and that gives us a thermal dissipation of 0.3 watts per square millimeter. David, this is roughly the thing that we're using as a starting point, as a thermal guideline, so to speak.
I see. Okay.
Amount of I/O size the tofu network eats up, which isn't a lot. We kind of have a sense of what we can use this as a reference ASIC. And good grief, self-evident functional modularity. The other is
Sorry,
Grace Hopper.
sorry, Rafi. One question. From last slide, you said ASIC slash node. That it mean two. It means that there are two different technologies.
No, sorry, ASICs per node. This is my huge effort to. So there's generally the way a supercomputer is organized, it's a node-based architecture,
Mhm.
and that you have replicated instances. In this case, you have 158,976 nodes, and the system as a whole takes 40 megawatts, and you have 2 of these ASICs per node.
Thanks.
Right. So, and the other one at the other end of the scale is this like giant Grace Hopper GPU, right? So the Grace Hopper super chip. Um, this thing combines 2 chips which are already big into a monster package. And what you notice here is the sheer amount of bandwidth between the die. This is what 8 terabits per second almost between the 2 CPUs. But you've got a sense of, okay, if I'm going to build a reference architecture, I need to make it functionally modular. This is sort of the small end of the HPC chip size. This is the large end of the HPC chip size today. And this is what we sort of started basing our thinking and planning off. And then the next question is, what do you do for package sizing? And Kamal from Intel sort of went off and did a survey of what kind of package sizes exist today. And roughly, you can kind of see that, at the NVIDIA again, at this, you can go from anywhere from 50 to 50 by 50-ish to, or at the high end, you can go to sort of 80 by 85 if you want to push your package sizes. So these sort of start giving us bounding boxes in which we can organize our thinking, right? We can sort of say functional modularity from the Fugaku, the upper bound on the sizes from the Grace Hopper, and we can sort of thinking if we're going to think of 1 or 2 package sizes, we should think of these 2 extremes of at 50 and 80. And roughly that's sort of the zone we started looking at. So I'm going to go a deeper dive, and stop for any questions. I mean, I've had a couple, and if anybody from our group is on, if you have anything else you'd like to add, please please speak up now, or please interrupt me now. Anu, or if anybody else is on. Okay, so this gives you a fairly, so we can take the Fugaku ASIC and split it. This is not the only way you can sort of cook up a reference architecture. I've sort of focused on one. There's another way where you can have this ring bus be a hub chiplet, the way Dreambig builds things. In this case, we've sort of had a chip. We've sort of gone for a partition where the network is embedded into the vector CPU. So you can think of it as I've got 4 vector I've got compute chiplets. You can, at the top level, you can sort of think of it and say, look, I'm going to take each function and make it a chiplet. And my HBM stays in HBM. I'm going to take my compute complex and make it a compute chiplet. I'm going to take the memory interface into the HBM and make it a chiplet. And I'm going to take the IO the IO that goes into goes into the node and make that those separate chiplets. So we glue all this together, you can see that there's a fairly straightforward, self-evident compute functional partition. What is interesting is you can sort of break it down into two types of chiplets. You can sort of break it down into square chiplets, which are dense logic, which can also be your accelerators, your GPU, and your heavy cores and everything else. And you can break it down to tall, thin chiplets. So your tall, thin chiplets are where IO forms IO is much heavier relative to the compute inside the chiplet. And so things like your NIC, your host controller, your memory interface, all of these things can be your tall, thin chiplet. So the interesting thing we believe is that HPC in your functional reference architecture, you can implement a wide range of functionality with just two types of chiplets. And you can sort of, for each chiplet type, restrict it to two sizes of chiplets. So we're beginning to sort of wrap our arms around saying, how do we controlling the complexity by saying you only need two types, and for each type you only need two sizes. And if you're going to build if you're going to build a chiplet, fit it into one of these two sizes. So that's sort of our proposal number one. Right? So if we want to take a reference compute chiplet, roughly it is, I sort of got two slides in back order, which is the size we think is like going to be around 11 by 11 square, which is about 121. The IO is going to be about 8 terabits, 2 terabits per side, and I actually show you why in a minute in the next slide. Power density is going to be about 0.3 watts per square, which gives you a compute chiplet dissipation power of around 36 watts. The core, we know what the core power and core wattage are. We're picking a 16 gig line rate, and D2D area and power is we're assuming the area is pad limit, and all of this will come to matter later. You can fit about 13 cores, and you get a bandwidth per core of about 615 gigabits per second. And all of this is important, but fundamentally, this is what a compute chiplet looks like, right? And you combine 4 of these compute chiplets to form one Fugaku ASIC. Where do we get the IO bandwidth? Roughly, if you sort of go into the Fugaku specs, you will sort of see that the IO for a compute chiplet goes in towards the towards tofu, towards the other towards the internal ring, and towards the HBM. And you cook all of that, you come to sort of roughly a max 2 terabits per side, a max 8 terabits per compute chiplet. So this is an example of this is a modular chiplet you can build. So if you're building a Fugaku like ASIC, you can sort of say my compute chiplet is 11 by 11 and it has these attributes. And if you put all this together, you can kind of say, okay, I can build a heterogeneous architecture if I can build a small chiplet which is square, which has got like my compute chiplets have a maybe not exactly 36 watts, maybe it's something plus or minus something plus or minus that. But now you got like a landing zone to aim for. You glue 4 of these chiplets, you glue memory interface chiplets and into a specific package. You can replace the HBM with something else, sort of a regular DRAM or whatever other kind of RAM you want in some other variant of this. But the point is now, if you're building an accelerator, you can replace one of your compute cores and slot in an accelerator which has roughly the same dimensions. We're not claiming that the package gets reused magically. It's simply saying, okay, if you're trying to build a special function hardware accelerator, if you're trying to build a new CPU, you've got a very specific landing zone to aim for in this. So roughly the small version of this maps onto what the Fugaku is, and the large version of this maps onto what the Grace Hopper is. So as sort of a generation 1 modular architecture proposal goes, 2 types of chiplets, 2 sizes for each type, and roughly 2 package sizes to accommodate all this. Any questions, thoughts? Does it make sense?
I like it.
Okay, thank you. And
Just
so,
one comment.
yes.
When you're looking at these sizes, did you look at your reticle utilization? 'Cause I think
No,
your sizes are off from that perspective.
I think you're right, and we have got to go back and tweak it. So I chose the sizes right now to sort of say, look, we could build what is being built. We can map to sort of, and I'll show you why I sort of zeroed in on that. What would you do in terms of reticle utilization? How would you change this?
Well, so I think that's a longer conversation, but I think if you look at, there are some natural sizes roughly, and what you're looking at here, your size is roughly a sixth of a reticle. There are slightly different aspect ratios that are near square that would be much more efficient from a manufacturability side.
So you think less than 11 by 11? You're thinking about 10 by 10 or something along those lines?
Uh, well, I think it's slightly different than that. I think you look at your reticle size and you want to do basically probably a third of a reticle on your X, and then you can choose to either do a half or a third on the Y, which would put you somewhere between sort of that 90 to 140 millimeter areas.
Oh, I see. So you're thinking we shouldn't be square. We'd want to be slightly off square.
I think you want to be slightly, or I think you want to look, because from a cost perspective, you probably want to be sensitive, because your highest cost will be you don't want to waste any reticle space in your manufacturing.
Got it. That's it. Thank you. That is very helpful. I don't think I can fix the damn thing by Monday, but it's
Yeah,
post
no,
Monday.
I think, Bapi, we did talk about this a little bit. This is the MFU factor, and how to get
Yeah.
it more
Okay.
precise. In general, it was like maybe squarish is reasonable, but yeah, and it also differs by technology. That so I don't know if we can hit a precise magic number there.
But we got to noodle on how to fix that idea, sort of accommodate that idea that if it varies by process node, and how do you sort of give people a constant factor to aim for? Any other thoughts? Thanks, Quinn.
So just as a reference, if you did like 10.75 by 12.75, you would have a
Okay. So
much higher, you're roughly the same size, but then you're going to get a high
high
reticle
yield.
utilization.
Okay. That's good to know. This being perfectly square is turned out to be less important than we expected. So that it should be easy to accommodate that. I just haven't modeled it.
Yes.
So the general idea is, the one thing I do want to point out is that the idea that you can now mix and match. You don't have to be, they don't have to be CPUs of the same type. Some of these can be hardware accelerators. You can change the memory interface. You can change the high-speed I/O. You can do all sorts of things, roughly all the goodness that chiplets bring you. The only difference is you're now asking for people to slot into very specific sizes, specific landing zones with specific I/O bandwidth, and that you're going to change this architecture generation by generation. Any other thoughts? Any questions? Okay, so the rest of the talk, we're going to spend a lot of time on something that came up over the last 6 weeks and really put us into it sort of opened up a whole new interesting way to slice this cake. It was the idea of how do you scale this reference architecture. So we've got this reference chiplet from Fugaku, and how do I scale it by how do I scale it across process nodes? What happens when I go to more advanced process nodes? And of course, when you're scaling it, you're sort of constrained by power and area, but you want to scale it while maintaining architectural balance. And by architectural balance, I mean roughly, what I mean is preserving the bandwidth per core. Roughly, you say if I'm going to stuff more cores in there, I need to add more bandwidth into this chiplet in order to maintain the bandwidth per core. So there are two scaling options we looked at. One is what I like to call technology-centric scaling, and the other is capital-centric scaling, right? And in technology-centric scaling, the idea is that, look, and the Professor Iyer was here last week, very well received talk, which kind of makes an argument for bond pitches are going to keep decreasing. The idea behind technology-centric scaling is that you can constantly, generation by generation, decrease the bond pitch. And if you decrease the bond pitch, you'll have more wires between your chiplets per mm of edge bandwidth, or you can go 3D eventually. But you have more you make use of advanced packaging, and you can go for wider, slower buses. And the advantage of going for wider, slower buses is that your power in joules per bit goes down as your line rate goes down. And your protocol complexity can go down, which means you have simpler PHYs which are likely to fit under the smaller and smaller bonds as you get bump area as you go down, right? So the intent behind technology-centric scaling is in each generation of this reference architecture, your chiplets move to a more advanced process node, your bond density increases, and you might even consider going for smaller, wider, slower die-to-die buses. That's the basic thought. The other option is for lack of a better word, what I'm calling it capital efficient scaling, where you don't actually change anything. You keep your die sizes constant. You keep your bump pitches constant. You just squeeze more stuff into each die from one process node to the next. You sort of say, I'm going to stick to a sort of like HBM. You kind of say, I'm going to stick to 55 micron bond pitches. I'm going to stick to 10 by 10 die, and that's it. That fundamental architecture stays stable for the life of for an extended period, for almost a decade. Those are our two options that we're considering. So the constraints on the scaling, there are two things, right? One, obviously, I got these process node parameters from TSMC, and I've captured it in terms of relative power. Bond pitches, we sort of said, look, there's a 30% improvement in bond pitches generation to generation. These are kind of ugly numbers, but that reality will be some actual integer, bond pitch that's manufactured by industry. And second thing to keep your eye on is this power density number, right? That we're assuming that this turns out to be pretty important, that power density can be improved by 20% per generation going forward. For the purpose of this analysis, I sort of kept die area as a constant for both technology-centric scaling and capital efficient scaling. Die power keeps increasing because we're assuming die power is primarily bounded by your ability to dissipate power. The area of a unit core keeps decreasing. I didn't do it I did linear scaling rather than square. And the power of a unit core also keeps decreasing. I didn't do absolute squares because obviously you're not going to get that efficient. So these are defensible assumptions. So fundamentally, what we know is that core count will increase with will scale with advanced process nodes, and the key question is how. How does core count scale, and how much does die-to-die bandwidth have to grow by? So if you look at technology-centric scaling, what you can see is roughly the total die-to-die bandwidth will grow from 8 terabits to 46, sort of an obscene 46 terabits. Roughly the number of cores will grow from 13 to 75. The interesting thing is you see that we're constantly reducing the die-to-die speed per lane. So we're sort of slowing things down from today's 16 gigabits per second down to 2 gigabits per second in the future, or maybe even slower. And you can, one of the interesting things is because you have an interesting combination of the amount of power and area goes down, because even though you're going for slower lanes, your bump pitches are closer, and you're using relatively less power. You'll see, excuse me, you'll see for the next slide. So, but fundamentally, you can sort of, this gives you a trade-off. Roughly, you're still fairly area efficient. You're using most of the area of your die for silicon, for, excuse me, for cores or die-to-die interconnectivity, and you're kind of maintaining architectural balance. Roughly, you're providing about 600 gigabits per core throughout this entire scaling, right? What happens if we keep things frozen? We just sort of say, look, I'm going to go at 16 gigabits per lane for the entire cycle for the next 5 generations. I'm going to stay at 55 micron bump pitch forever. How does this whole thing work out? It's not too bad, right? You spend more on die-to-die power than you would, I think, on, you spend, so here you spend 23 watts for die-to-die power, here you spend 31 watts. So in theory, there's less wattage for cores. So that gets reflected in the reduced core count number in the out years, right? But fundamentally, these are your two extreme options. You know, sort of squeeze as many cores, as much compute as you can into a die by reducing, by going for slower, fatter buses. Or you can say, look, I just want like a HBM style, I want a predictable landing zone for all my chiplets. I'm going to keep constant line rate, constant bump pitch. But I'm willing to pay a price on the number of cores and the amount of compute logic I can squeeze in. And again, here we are maintain rough architectural balance, which kind of say like we provision enough IO bandwidth so that you end up with around 600 gigabits per second per core that you put into the compute chiplet. Any questions, thoughts? So the real interesting thing is, more if you can't improve power density, you get whacked much more badly than if you fix your IO line rate and bump density. So if you kind of say, look, if I'm going to squeeze in, if I'm going to go for maximum bond density, this is the blue line sort of shows you the growth of cores per generation. If you then say, I want to be capital efficient, I want a stable manufacturing line that has fixed sizes, a discrete number of sizes, and I'm willing to pay a price in terms of the number of the compute density, you get this red line, which is what we call the capital efficient line. But if you can't improve your thermal dissipation density by 20% and you're capped at 10%, that actually has a far more significant impact than freezing bond density at today's levels. You sort of really, you get fairly quickly become power constrained in your chiplets. So this ends up having a far bigger effect than than freezing the bump density. So in my mind, you've got two ways to go forward, and there's sort of compelling, reasonably interesting arguments for both. If you go with capital-centric scaling, you've got a limited discrete set of die sizes and packages. You've got fixed mechanical and thermal properties. Each generation kind of revs the architecture HBM style, where HBM2, 2E. So you sort of say HPC1, HPC2. And in my mind, chiplet and ASIC designers can aim a product for specific landing zones for a generation. We hold it stable for several years, and you reduce packaging and assembly complexity. On the other hand, I want to thank Professor Iyer for this slide and his students. If you sort of say, I want to go for technology-centric scaling, you're sort of squeezing out everything chiplets have to offer. You can now go in and say, there's going to be effectively no difference between on-die and off-die connectivity. So what I can do is I can go for much smaller chiplets. I can essentially form a sea of chiplets, and I can squeeze in as much, I can use I can squeeze in as much chiplet compute into each chiplet as possibly can, because I'm using I'm using everything packaging technology has to offer. And the price you pay is more complex packaging and assembly that you will hopefully solve with automation. So fundamentally, I feel like it is kind of the equivalent of risk versus CISC for packaging. You've got two attributes to scale out your reference architecture, and we need to hunt for some metrics on which way we choose, or it's some combination of the two. You sort of say, do I want to go for increasing bond density? Do I want to go for a constant bond density where do I want to go for narrow fast buses which are significantly faster than on-die buses? Do I want chiplets? Ultimately, one interesting thing that the technology-centric approach enables is a much higher, is it about a relatively higher compute density, about 10-20%. It being a simple model. And ultimately, you can sort of push architecture towards a sea of small cores, so the way Professor Iyer showed last week. Or you can sort of say, I'm going to stay with constant die size and increasing functionality at a constant bandwidth per core. The production line is where the capital efficient scaling may give you some production and design complexity is where capital efficient scaling gives you some advantages in my mind. You've got a stable physicals for multiple generations, so designers can aim for something solid and something stable. And in terms of packaging complexity, you would require technology-centric scaling requires significant tooling and automation, which is kind of what you want in a domestic packaging factory, a technology edge. And capital efficient scaling is kind of an extension of today's complexity. Any questions, thoughts? So in terms of next steps, what we'd like to do is go off and refine this reference architecture for HPC, share it with a larger HPC community, chiplet vendors. We need some rational specs, and maybe Quinn's, I think, go back to Quinn's thought, which Anu says we've hit, which is the idea of looking at reticle sizes as well. How many chiplet sizes should we support? Should we support chiplet sizes which are multiples of 4 of one another in some sense, so that the dimensions you can sort of mix and match? We have to stress test this by validating against known HPC use cases. Identify the drivers and dependencies of the scale. Thermal density appears to jump out. David, this is what I was referring to when I said thermal density way back. And eventually, I think there's room to apply this idea to other domains, medical devices, automotive, or networking. Right. So in terms of open standards, as with anything else, I think it's essential for chiplets. What we attempted to do was generate guardrails for packaging and assembly, so that you can make room for automation. Thanks to some excellent contributions from the members of the working group, I think we have a fairly decent reference modular chiplet architecture proposal, and which we hope to extend to other domains. That's basically it. Any questions, thoughts?
I think it's fundamentally, I think you took the right approach. I think some tailoring, to the exact specifics, but I think fundamentally I agree with your approach here.
Oh, excellent. Thank you. I've got to make a shortened version of this for Monday, slice off a few slides at the front end and the back end. Anu, anything else you'd like to add? Oh, sorry, Bijan, go ahead, please.
No.
Bobby, when you say Monday, is that a specific meeting on Monday?
Monday at Semicon is when this whole effort is Subbu's whole effort is reporting out all the twigs, not just this one.
I'll call and talk to you on this.
Sounds good, Bill.
Yeah, Bapi, my sense, this is Cash, is I think you made a very important point, which is if you go with a more aggressive packaging approach, right? That's not what the way HBM is. The reason HBM is they want multiple manufacturing and billions of units, right? So it's all about investing in that and then just doing that, right? Which is how you make money doing billions of units. In our case, for onshoring, it would make sense to be really pushing that packaging technology as a competitive advantage. Just my sense.
Exactly.
So I think that's so you because the chiplet individual volumes are not going to be like traditional memory, right? And performance does matter. So I thought the professor's chat, even though it's very leading edge, was quite compelling, right? So the more you can push that with a real solid, high quality packaging facility and services, that starts to give you a competitive advantage over just saying we have to dumb this down for a broad market like memory devices, right? So I'm just giving you my 2 cents of what I saw. I thought it was a great overall presentation, but I would just emphasize, hey, this gives us an opportunity to have a strategic advantage over just building everything, right? So because it's optimized for HPC, et cetera, and where this technology is going. Just my sense.
Yeah, so when I started, I sort of said, oh, I fell in love with the capital efficient scaling idea, but the more Professor Iyer beat me up every day, I sort of seeing where he was going with increasing bond density. So it's not as clear cut to me. I think the thing about HBM in my mind is people are able to plan around it in an interesting way, in a way that's much harder if everything is in flux. But
Yeah,
like
but
you
you
said,
can
there's
still
this
fix
huge
the
strategic
sizes.
advantage.
You can still fix some of the sizes, right?
Right.
Just not fix the bond pitch and things like. Anyway, I just
I agree with you. It's just like there's
yeah,
a
yeah, I
compelling
think
case to be made for a technology based thing. Seriously.
right,
So um,
right. Because if we're trying to build something that is suitable for hundreds of millions of units a year, build the same thing. But I really don't think that's what we're trying to do. Is because that doing it here will never be competitive with doing it in offshore places, right? Whether it's India in the future or Vietnam or wherever, right? So we need something that's leading edge, but that's U.S. based. So anyway, that's just my sense on that. So it depends on which angle what problem you're also trying to solve, right? A practical problem, which is for this very advanced technology, we need something in the US and it's strategic, and HPC is where it's at, right? From a big picture strategic standpoint.
right.
So I think that's where things would fit better. Um,
Yeah, I think there's two aspects to this. One is HPC is a little more niche than probably memory, which is much higher volume, and millions of people use it as a product. Um, but in order to keep costs relatively reasonable, right? And the whole point was bring manufacturing to the US and make it such that if you make it more modular as opposed to highly custom, the costs can be kept down. So this effort was to go towards that, and starting with a reasonable 55 micron pitch to a 45 micron pitch, I think seems very reasonable at this point, but with a roadmap to see how it goes down, as Professor Iyer presented, to a 10 micron bump pitch, which he thinks is highly possible sooner than later. So
Thanks, Anu.
Bappy, this is
Yes.
Michael Byrne here. Bappy, just to test your thesis on going towards the HPC, you're talking about extending to other domains. Is there any chance you would learn more from the other domains, such as medical devices, which may be low power? There may be demands in there. HPC, a lot of the HPC stuff has driven chiplets at this stage, but are some of those other domains going to change it in some way?
Oh, 100%. What I should have made clear is that it's going to be different reference architectures, not one universal reference architecture.
Absolutely, yeah.
Yeah. So, but yes, 100% in terms of like the medical devices may even make the case for depending on whether you're going after wearable medical or high performance medical, you make the case for different constraints on the die to die and the total power. Yeah, so the short answer is absolutely. But the
I,
general answer is if you constrain the physicals, you can still meet the functional performance requirements of the target market and yet make reasonable room for packaging and assembly automation. That's the pitch here.
okay.
So by constraining it to physical, with tight physical sizes, we still think we're giving you reasonable performance per chiplet and mapping to something that is very close to either the two sort of popular high performance chips in the market today. David, does that answer your question, the original question way back of the thermal stuff?
Yes, thank you.
All right.
So, Bapi, realistically, this is 3 years away, right? So, a good other input for you might be to talk to the Intels, Nvidias, AMDs of where they see their product in 3 years. Just as a you know. As you know, working with the government and getting a factory built, I mean, it just takes time. Uh, so if it's 2, 3 years away from now, let's say, even if tomorrow, if even if Monday was T0, um, you want to make sure that it's structured for the right technology for HPC or medical for 3 to 4 or 5 years out, right? That's the other point that so
Right.
it'd be
And
interesting to make the study. But 7 nanometer may not be that right technology. So I think you might want to center it at a tighter technology for something that starts in
yeah.
3 years.
Wait, am I still sharing my screen? Yes. So I think the what I think 5 or 3 is a reasonable thing, and roughly, we're showing a reasonable increase in compute density comparable to what the increase in compute density is an estimate of how the architecture will scale in terms of I/O and performance. So to sort of say, hey, you're going to go, you're going to hit to about 3 times the core density for this same size die. That's what we're using as a measure of scaling.
So from my perspective is that if we just start thinking about pitch, um, getting lower and lower pitch, the first couple generations may be possible, but then it get much more expensive and difficult. So then you have to move over from the reducing pitch to the other capital centric scaling. So that I think there's a switch over. There's a there's a switch from one to the other as you go out into the future.
Oh, I thought it would be the other way around, that you would go capital centric and then go to advanced technology, but you're saying it's the other way around. Okay. Thank you.
I'm just thinking from the packaging perspective, in the sense that the pitch reduction from the packaging tools capabilities will get more and more difficult.
Yes, it makes total sense. All right. Any other Krithikesh, anything on your mind?
No, I think I think what I did discuss this with Professor Iyer, and basically the idea was yes, we have to go down in bonding pitch, and at each bonding pitch, we'll also be doing the capital F scaling. So what he was saying is that capital F scaling will anyways be happening, but at the same time, we should be doing the technology
Yeah.
centric scaling because that gives us that strategic advantage
Yep.
that was needed. Yeah.
All right. If there are no other questions, thanks all. The feedback was really helpful. I'm going to tinker with this deck and knock it off before Monday. Thank you.